Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA, which looks at the cement industry's response to climate change around the world and other topics of interest. I'm Ian Riley, CEO of WCA, and your host on the Clinker Factor. The cement industry has been traditionally using three levers to reduce the carbon footprint of cement, namely energy efficiency, alternative fuels, and reducing clinker factor. But those don't get us down to decarbonisation. They only get us part of the way, perhaps only another third of the way. And so now we're looking for other technologies that can help to decarbonise the industry. And one that's been getting a lot of attention recently is mineralisation or carbonisation or carbonation, i.e. the storing of CO2 in minerals such as aggregates and concrete. And today I'm talking to Dr. Paula Carey, a founding director of Carbon8 Systems, which was formed in 2006 with her colleague, Professor Colin Hills from the University of Greenwich. Paula is a geologist with a PhD from the University of Kiel. So Paula, welcome. I wonder if we could kick things off by asking you to introduce yourself and how you came to be working at least in the edge of the cement industry.
Thank you very much, Ian. Yes, I'm Paula Carey, one of the founding directors of Carbon8 Systems. I used to be an academic at the University of Greenwich, and as you say, a geologist by training. But whilst I was at the university, I sort of changed from mapping metamorphic and structural geology in the Scottish Highlands to looking at geology as it could be applied to natural resources. So through that, we developed a Centre for Contaminated Land Remediation, and we were studying cement stabilisation and solidification. And my colleague, Colin Hills in particular, thought, well, actually a good way of accelerating normal cement stabilisation is to mix the cement and the residues or the contaminated soils with carbon dioxide at the same time, so that instead of getting cement hydrates, you get calcium carbonate forming from the calcium silicates and calcium oxides. So the technology, accelerated carbonation technology, developed from cement stabilisation of contaminated soils and wastes. And that's how I got involved, really.
And so when you first started Carbon8 Systems, were you thinking more about waste treatment than you were about absorbing CO2?
Yes, definitely. We started off as treating contaminated soils with cement, but using carbon dioxide. But obviously, as we've progressed, the use of carbon dioxide has become the more important USP, if you like, for the development of the technology.
Right. So could we just look at the technology itself? You referred to it earlier as accelerated carbonation technology. So can you explain what that is and how it works?
Yes, of course. First of all, I'd like to talk about the few words you used at the beginning: mineralisation, carbonation, and carbonisation. We rule out carbonisation because you can think of that really as being the formation of carbon, so burning things, I'd like to say, is that. So carbonation is often spelt incorrectly to end up being carbonisation. So it's mineralisation and carbonation, where you have calcium or magnesium compounds in either rocks or in industrial residues. But if you get the conditions right, worked with carbon dioxide to form calcium or magnesium carbonate. So you can think of carbonation or mineralisation. So the words are more or less interchangeable, although I like to think of mineralisation being carbonation of rocks. So I'll talk about that in a few minutes, but carbonation being the reaction in residues and things. But it's nature's way of permanently locking up CO2. So it's nature takes CO2 from the atmosphere and forms calcium carbonate, so limestone and dolomite. But what we do is control and manage that natural process, so it takes minutes as opposed to millennia in the geological environment.
So just to make sure I'm clear on that, so we're talking about either calcium or magnesium, and then the carbonation of that to form calcium carbonate or magnesium carbonate. Is that right?
Yeah, you think of it simply in the cement world. If you're carbonating cement, particularly with accelerated carbonation, you're taking the lime or the calcium silicates and you're reacting them with carbon dioxide before they hydrate. We would count it as carbonating green cement. So the advantage is that the carbonation reaction of those calcium silicates happens almost instantaneously, rather than the hydration reaction, which obviously takes hours, days, weeks to go, or can be still going after several years. So, but carbonation will happen very quickly if you get the conditions right.
So with carbonation, given the correct conditions, do you get a much more complete reaction of the cement than you do with a regular hydration process?
Yes, absolutely. The reaction can go to completion in a matter of minutes, say 15, 20 minutes. Obviously, it depends on the fineness of the material you're treating. With a nice fine-grained 52.5 type cement, it will happen very quickly. We quite commonly do a nice little demonstration where you put a bit of damp cement, so using a water solid ratio of about 0.1 or 0.2. So mix a small amount of water with your cement, put it in a plastic bottle of some sort and squirt CO2 from a bicycle pump. And before your very eyes, you can get carbon capture, because the CO2 in the bottle, if you seal the lid, obviously, carbon dioxide in the bottle will be absorbed into the cement in a matter of minutes. But you have to be careful because it's an exothermic reaction, so the bottle can get very hot.
So can you explain how Carbon8 Systems is using that process and what products or services you're offering to the cement industry?
Well, having worked principally with cement and thinking about carbonating cement, we realised that there are a lot of industrial residues which contain the same magnesium, but more particularly calcium compounds. So principally lime, but also calcium silicates, which would react with the CO2. So you're looking at things like steel slags, cement residues, both bypass dust and kiln dust, and then residues from energy from waste, both the bottom ash and the fly ash or the air pollution control residues. And then things like paper ash or biomass ash can be variably reactive with CO2. As it is applied in the cement industry, we're using the technology to treat the cement bypass dust. So, and obviously, cement bypass dust is an increasing issue as the cement industry moves more to refuse-derived fuel, because you have to remove things like the chlorides from the cement. So as the amount of bypass dust increases, then our technology has more application. So we take the two waste streams from a cement plant, the CO2 directly from the flue gas and the cement bypass, and we react them together, and through the engineering and the processing of the two materials, we produce a lightweight aggregate product.
And this aggregate product is used in the normal concrete markets, or what are the main applications for the aggregates?
Yeah, they're mainly in a bound application, so concrete. It can be used in some other specialist applications such as pipe bedding, or in one of the applications we're looking at is green roofing, for example, or horticultural products. because it's commonly quite high in potassium, so that's quite useful. I mean, it's not as strong as a granite because it's formed over 15 minutes rather than millennia that a granite or a flint gravel will have formed. So you wouldn't expect to use it in high strength concrete, but there are a lot of applications in ready mix or in precast where it's very applicable. Principally, it's used in concrete blocks as a replacement for example, coal bottom ash, which of course now we've got no coal power stations. We don't have the fuel bottom ash that was traditionally used in concrete block manufacture.
Right. And so at the moment, you're applying the technology to the CKD, which is generated, as you say, when cement plants use more refuse-derived fuel. Typically, that would be what, about 2% of the total production, something like that, the bypass?
Something like that, yes.
So at the moment, then, the carbonate systems technology, if applied at a particular cement plant, could produce aggregates from that 2%. Would that be roughly the same weight as the 2% in the aggregates? I suppose you're adding CO2 would increase the weight somewhat, wouldn't it?
You increase the weight a little bit, but in the treatment of cement bypass dust, we probably produce, well, the maximum uptake we've seen in bypass dust is about 30%. Mm-hmm. So you're increasing the weight by that 30%.
Right,
okay. So the capacity of a typical plant that we would install at a cement works is around 12,000 tonnes a year. So a cement plant would produce between 8,000 and 12,000 tonnes a year of CBD. So you would, at the best plants, you would capture another 30% CO2, but more typically it's between 15 and 20% uptake.
Right. How would you see that scaling beyond that 2% CKD?
Well, even with that sort of 2%, we still think that there's the potential to capture within the cement industry, if we were to treat all the CBD produced, around 150 to 190 million tonnes of CO2. So just deploying to all the cement plants that are generating bypass dust, you start to actually make a reasonable impact. But actually, of course, we can treat other reactive residues as well. And if you add up all the available residues, you could reach just about a gigaton of CO2 per year captured through using accelerated carbonation. That doesn't include a lot of historic deposits of these sorts of residues, steel slags and reactive fly ashes, or even cement kiln dust.
Right. Yeah. So you've got two feed streams there that you're talking about. One being the kiln bypass dust that's being produced currently, the other being other residues. And you mentioned some of these earlier in terms of slags and fly ash and so forth. So can you tell us a bit more about that?
Yes, our initial commercialization of the technology in the UK was through the treatment of air pollution control residues that come from energy from waste. So to treat the flue gas from energy from waste. Have you got the dog barking in the background?
I'm afraid we do have the dog barking.
Yeah, so this is where you inject lime into the flue gas of an energy from waste plant, an incinerator. And that lime collects things like the sulfates and chlorides in the flue gas, is collected in a filter bag and then is transported to a central site treated with pure CO2. So that those plants have been in operation since 2012. But they use pure CO2, which is actually expensive and in some cases has been in short supply. So in 2018, we decided to move to using direct air capture and direct capture from the flue stack. So flue stack CO2 is about 10% by volume. And we found that we could use that directly without having to go through the expensive purification. And that's really one of the advantages of a technology such as ours, where you can capture the flue gas CO2 without having to go through all the expensive purification, liquefying the gas so that you can just transport it.
Yes, I think when we look at the economics of CCUS generally, then this purification or concentration of the CO2 is one of the significant costs.
Absolutely.
So that any technologies that are capable of using, let's say, run-of-the-flue concentrations, as you say, 10% or perhaps 20% in some cases, have a huge financial advantage over those that require concentration. How were you able to do that? What was the key part of the technology that allowed you to use that lower concentration gas?
Well, one of the things that we saw when we were working in the laboratory was the problem of using pure CO2. As I said, the reaction is very quick, and what happens even with fine-grained materials is you get a blinding layer. The calcium carbonate forms very quickly around the grains, and further CO2 can't then penetrate through that shell. But we found that if you use dilute CO2, you could actually overcome that slowing of the reaction. So it's the less concentrated CO2 diffuses through the grains better. You also don't have so much of a problem with the exotherm. So when you're using pure CO2, it can get very hot. And the interesting thing about CO2 is its solubility in water is greater at lower temperature. So as you heat the process up, the diffusion of the CO2 through the liquid interface into the solid is slowed because you don't get as much CO2 dissolving. Okay,
so in fact, the nature of the reaction was benefited by having the lower concentrations.
Yes, to a certain extent, you lose some of the overall speed. I mean, the ideal concentration might be about 50%, but we've seen that we can work down to 10%. It's all about how you deliver that CO2.
Right, and you've been delivering your solutions in a containerized form. Perhaps you could tell us a little bit about that, and does the concentration of CO2 affect the size of the equipment that you have to use?
Yes, we've deployed our container down to the VCAT cement works at Montpellier. It went down there in 2020 in September. So we've managed to get down occasionally despite the pandemic. The capacity is limited to the scale of the mixer that you want to use, which to a certain extent is controlled a bit by the exotherm. So it's all designed to fit the amount of residue that you've got rather than the CO2. So the main issues are making sure that you can deliver the CO2 in sufficient quantity to keep the reaction going. So it's a matter of designing the pipe work and those sorts of things.
Right. And what do you see has been the advantage of the containerized solution? Is it speed of deployment or other aspects?
Oh, definitely speed of deployment and installation. You can install our 40-foot shipping containers without having to have complicated foundations. It's very much a plug and play solution. All you need is supply of water and electricity and stabbings into the flue stack. So it can be retrofitted to existing plants.
What's the overall impact on the CO2 footprint? Perhaps if we can take CKD as an example, how do you assess the overall impact on the CO2 footprint?
Well, we're looking very much at the idea of producing low carbon building materials. So if we look at the footprint of the aggregate product and we take into account the amount of CO2 captured, that's relatively easy to measure, then look at the energy required to do that capture. With mineralisation or carbonation in general, that energy requirement is always quite low because it's an exothermic reaction. You don't need to put in lots of energy to make the reaction happen. The only energy you require is to, in our case, is to move the materials around and mix them in the CO2 atmosphere. So if we take that into account, and then you look at things like the water consumption, the transport of the materials around, you can soon work to giving a life cycle assessment or a carbon footprint from the material that is certainly negative. And for some of the more reactive cement residues, you can have an LCA of around minus 150 kilograms of CO2 per tonne.
That's per tonne of aggregate.
Per tonne of aggregate, yes. That's being a bit pessimistic. We can do better than that, but until we get our LCA analysis is still preliminary. We need to get it validated and an audit on it, but that's the sort of order that we're looking at the moment.
Okay. And perhaps just to close, could you give us your view on how the wider market and technologies for carbon utilization in essentially low carbon building materials will develop?
I think it's an exciting time to be in mineralisation and carbonation. I think, as we talked about earlier, particularly the cement industry is very keen on the idea of carbonating things, and I think it's important for the short-term ideas of decarbonisation that we implement some of the technologies that are available for reducing the carbon footprint of buildings via mineralisation. Mineralisation is particularly good because it's a low energy system and you're not having to use a lot of renewable energy, whereas some of the other utilisation technologies require that energy input to transfer the CO2 into more complicated molecules. So mineralisation has a lot of advantages in that area, but no utilisation technology is going to stand alone. I think it's all about using lots of different technologies to make small increments, but we can do that now rather than waiting for the infrastructure that's required to do CCS. So carbon capture and storage is an imperative for the big CO2 producers because it involves so much CO2, but we need the infrastructure to be able to progress that, and it's expensive. The capture of the CO2, the purifying of the CO2, and then its transport is expensive. And utilisation is there actually to make the whole business more cost effective because you've got products to sell at the end.
Yes, absolutely. I couldn't agree more. I think that CCS, as you say, is the only technology we have at the moment that's proven at scale, but it's clearly very expensive. And in the cement industry, we really worry about that. And energy costs currently are the largest single cost in producing cement, but in the future, it could quite easily be the decarbonisation costs that become the highest. And the way in which we decarbonise will have a big impact on competitiveness in the future.
The cement industry has a real big problem because cement plants are based on the geology, not on the development of where infrastructure might be for CCS.
Yes, absolutely. And 90% of cement, of course, is produced in the developing world, and solutions that require a very large upfront investment and that are expensive to operate seem unlikely to be acceptable in most places.
Absolutely. So
Paula, thank you very much for talking to me today. It's been a fascinating conversation, and I wish you well with the development of carbonate systems in the future.
Thank you very much, Ian. It's been a pleasure.